previous class we already discussed about different types of magnetic materials, and today we will discuss about Earth's magnetism. That means how Earth behave as a magnet and what are the properties or characteristics of Earth's magnet that we will discuss today. So let us discuss about Earth's magnetism. Okay, Earth's magnetism. As we already know that when we suspend a bar magnet freely, it will align itself along the direction of geographical north and south. That means if this is a bar magnet and I will allow it to suspend freely, I will suspend it freely, then automatically it will align itself along the direction of geographic north and geographic south. That means the north pole of this bar magnet will directed towards what? The geographic north pole, and the south pole of this bar magnet will directed towards the geographic south pole. That means, as we know, a bar magnet is only deflected by an external magnetic field. That means when we suspended it freely, in the absence of any external magnetic field, but still it gets deflected. That means there must be an external magnetic field. So, and this phenomena and this property of bar magnet is shown every place on Earth's surface. That means there must be a magnetic field present all over the Earth's surface. So due to the directional property of bar magnet, it is conclude that our Earth is behave as a magnet, and this was first proposed by William Gilbert. Clear? So the evidence for Earth magnetism is the directive property. Of bar magnet, or due to the directive property of bar magnet, it was evidence that the Earth behave as a magnet, and as the Earth behave as a magnet, then it must have some properties. So due to the directive property of bar magnet, we conclude that Earth is behave as a giant magnet. But what is the cause of Earth's magnetism? Anciently, scientists thought that as there is a large amount of molten metals present in the Earth core, due to these molten metals, the Earth behave as a magnet. But according to Curie's law, as temperature increases, the magnetism or magnetic effect of any magnet will decrease or disappear. So as the temperature of Earth's core is very large, so all the metals present over there must have zero magnetic effects. So this cause for the Earth magnetism was wrong. Next, scientists proposed that as the cosmic rays comes from different stars or terrestrial objects which carries ions and charged particles, and that cosmic rays carries ions and charged particles enter to the Earth's atmosphere, and as Earth revolves around its axis from west to east direction, so its atmosphere also gets revolved, and the charged particle present in the atmosphere of Earth it also starts moving, and due to the motion of the charged particles and ions, there is a current produced in the Earth's atmosphere, and due to that current it may be create a magnetic effect, and due to that magnetic effect Earth behave as a magnet. So as we already know that if this is our Earth, this is the axis about which Earth is revolving from west to east direction. As for this, we know this is the north, this is south, and this is east, and this is west. So as Earth rotates from west to east direction, this axis is known as Earth's geographical axis, and this is known as geographic north, and this is geographic south. Clear? And Earth rotates like this. So the atmosphere surrounding the Earth will also rotate like this, and due to the rotation of Earth, all the particles or charged particles or ions present over in the Earth's atmosphere will also start revolving like this. So due to along this direction, as the charged particles start revolving, they produce a current which is in clockwise direction. So due to clockwise direction, if we crawl my finger along this direction, there will be a magnetic field produced which will along this direction. As the earth revolve like this, okay, the earth revolve like this from this to this. So along this direction earth revolves. So as the earth revolves like this, the atmosphere also revolves along this direction, and due to revolution of earth's atmosphere, all the charged particles present in earth's atmosphere also starts revolving and they constitute an electric current, and due to this current there will be a magnetic field whose direction will be like this by right hand thumb rule, and due to this magnetic field the earth behave as a magnet. And as we suspended a bar magnet, its north pole directed along the geographic north pole and its south pole is directed along the geographic south pole. That means as is north pole of a magnet is most attracted towards the south pole of another magnet, and the south pole of a magnet most attracted towards the north pole of another magnet. So as the freely suspended bar magnet directed its north pole along the geographical north pole, that means along the geographical north pole there must be the magnetic south pole of the earth's magnet. That means near the geographic north of the earth there must be the magnetic south pole of the earth. That means if we represent the earth as a big bar magnet which will be like this, this will be the magnetic south pole and this is the magnetic north pole. As if we here present a magnetic needle, it will be remain like this. This will be the north pole and this will be the south pole. Clear? That's why the magnetic south pole of earth is close to the geographic north pole and the magnetic north pole of earth is close to the geographic south pole. And you can observe that the magnetic south pole and geographic north pole and magnetic north pole and geographic south pole of earth never coincide with each other. They deviate from each other by a very small angle which is nearly about 11.5 degree. Clear? And the vertical plane which pass through the geographic north south is known as geographic meridian. Vertical plane through geographic axis is called geographic meridian. Okay. And similarly, the vertical plane which pass through Earth magnetic axis is called magnetic meridian. Okay, the vertical plane through geographic axis is known as geographic meridian, and the vertical plane through Earth's magnetic axis is known as magnetic meridian. That means this axis is known as Earth's geographic axis, and the vertical plane which pass like this. The vertical plane which pass like this along Earth's geographic axis is known as geographic meridian, and as this is the Earth's magnet, this south and north pole are the Earth's magnetic south and north pole, so the axis passing through this is known as magnetic axis, and this is known as geographic axis. And the vertical plane passing through this plane, this axis, the magnetic axis, is known as magnetic meridian. As there is an angle of deviation nearly about 11.5 degree between geographic axis and magnetic axis, so this angle is also between the magnetic meridian and the geographic meridian. So the deviation between the geographic meridian and magnetic meridian is also nearly about 11.5 degree. Clear? So the vertical plane that pass through geographic axis is known as geographic meridian, and that the vertical plane pass through the magnetic axis is known as magnetic meridian. And also the circular line which is perpendicular to the geographic meridian like this is known as geographic equator. The circular line which is perpendicular to the geographic axis is known as what? Geographic equator. So this is known as geographic equator. And the plane, if this will be considered as a plane, then it will be the geographic equatorial plane. Clear? Similarly, the circular line which is perpendicular to the magnetic axis is known as magnetic equator. If this is the magnetic axis, and for this it will be perpendicular, so the magnetic equator will be like this. Okay, and this plane will be known as magnetic equatorial plane. This is known as magnetic equator. Okay, so this is geographic axis, and the vertical plane passing through this is known as geographic meridian, and the circular line which is perpendicular to geographic axis is known as geographic equator. Similarly, this is magnetic axis, and the vertical plane passing through this is known as magnetic meridian, and the circular path which is perpendicular to this magnetic axis is known as magnetic equator, and the plane along this magnetic equator is known as magnetic equatorial plane, and the plane along geographic equator is known as geographic equatorial plane. Clear? And from this diagram we already know that the Earth magnetic south pole is near to the geographic north pole, and magnetic north pole is close to the geographic south pole. That means the magnetic north pole is present along the southern hemisphere of Earth, and the south pole of the Earth's magnet is present along the northern hemisphere of the Earth. Clear? And the magnetic axis and geographic axis, or the magnetic meridian and geographic meridian, both are deviated from each other by a very small angle, 11.5 degree. So this is how the Earth behaves as a magnet, and what are the terms regarding the Earth's magnetism. Clear? Okay, now discuss about magnetic elements of Earth. So first we will discuss about declination. This is denoted by theta. Okay, what is declination? This is the angle between Earth's magnetic meridian and geographic meridian. Okay, at any place. Here, so declination, this is the angle between Earth's magnetic meridian and geographic meridian at any place. That means, as we already discussed, that if this is our Earth planet and this is the geographical axis and this will be the magnetic axis, then the angle between this angle, the vertical plane will pass through this geographic north and south, is known as geographic meridian, and if this is the magnetic south and north, and the vertical plane pass through is known as magnetic meridian, so the angle between these two, this will be known as theta, which is known as a declination. And we know this is nearly about how much? 11.5 degree. This angle is fixed, but from place to place this angle will vary, because if this will be known as the magnetic meridian and this will be known as the geographic meridian. This will be like this. If someone view these two from this side, the angle will be this much, But if someone view from this side, like this, if I rotate this light, then the angle will be very less. So the angle is fixed, but from place to place, as we move from place to place on the earth surface, the angle will be different. If someone look at from this place, the angle will be this much. If someone look from this place, the angle will be decreased, and someone look from this place like this, the angle will be very small. So the angle between the geographic meridian and magnetic meridian is known as declination or theta. This is denoted by theta, and this is the angle. That means if this is a place and this is the magnetic meridian at that place, and this is the geographic meridian at that place. Okay, then this angle between the magnetic meridian, this is magnetic meridian, and this is known as geographic meridian. Then this angle is known as theta or declination. Clear? The angle between Earth's magnetic meridian and geographic meridian at any place is known as what? Declination. And this is nearly about how much? 11.5 degree, but fixed. But from place to place, the angle of declination will vary. It is fixed between the two axes of Earth, geographic and magnetic. But from place to place, as we already saw, from place to place, this angle will vary. Clear? Next, we will discuss another element of Earth, that is known as inclination. So now discuss about inclination or angle of dip. Discuss about inclination or angle of dip. Denoted by phi, or this is known as dip. Okay, what is inclination or dip? This is the angle made by Earth's net magnetic field with the horizontal direction at any place on Earth's surface. Okay, so inclination or dip is the angle made by Earth's net magnetic field with the horizontal direction at any place on Earth's surface. That means if this is our Earth, and we know at this portion, this is known as the south pole of Earth's paramagnet, and this is known as the north pole. So the lines of field lines of Earth's magnet will be like this. Start from north to south, and within it will be from south to north. Okay, so as these lines are traveling along this direction, so the magnetic field direction will be tangent to this line at any place. From this place, this will be the direction of net magnetic field due to Earth's magnet at this place. This will be the direction of net magnetic field due to Earth's magnet, and at this place, this will be the direction of net magnetic field due to Earth's magnet. So the net magnetic field and the direction of horizon at any place on Earth's surface is known as what? Inclination. That means if at this particular place I want to calculate the angle of inclination or dip, then what is that angle? That angle is between the direction of net Earth's magnetic field at that place and the which makes with the horizontal direction. So at here the horizontal direction will be like this, which is perpendicular to the vertical. Here is the vertical direction. So the horizontal direction on Earth's surface at this place will be like this. This is the horizontal direction at this place, and this will be the vertical direction for this. So at this place, if this is the horizontal direction, then this angle, this small angle, if this is horizontal direction and this small angle is known as what? The inclination or angle of dip at this place. And this place also, if this is the horizontal direction, then this angle is known as inclination or angle of dip. So at any place on Earth's surface, if we want to determine the inclination at that surface, at that place, then it will be what? The angle of the between the Earth's net magnetic field direction at that place with the horizontal direction, and this is denoted by what? Phi, or this is also known as dip. Clear? Then what is the value of phi at magnetic equator of Earth? As at the equator, if this is the complete Earth, this is the equator. So at this equator, the direction of magnetic field will be along this, and this is also the direction of horizon. So the direct angle between net magnetic field and horizontal direction at equator is 0. So the angle of dip or inclination at equator is 0, and at the pole, as the net magnetic field direction will be like this, and this is the horizon. So the angle between these two will be 90 degree. So we have to remember that dip is 0 at equator and it is 90 degree at pole. That is both north and south pole. You have to remember these two values for your examination. Dip is 90 at pole, that is both north and south, and it is 0 at equator. And this is the definition of inclination or dip, the angle made by the Earth's net magnetic field with the horizontal direction at any place on Earth's surface. Clear? Okay, so now let us discuss about the third magnetic element of Earth's magnetism, that is horizontal component of Earth's magnetic field. Horizontal component of denoted by BH. So it is a horizontal component of Earth's magnetic field. According to the name, this is the component of net Earth's magnetic field along the horizontal direction at Earth's magnetic meridian. This is known as, it is the component Earth's net magnetic field along the horizontal direction of Earth's magnetic meridian. Okay, it is the component of Earth's net magnetic field along the horizontal direction of Earth's magnetic meridian. That means, as we already draw a picture here, if this is the Earth's magnetic meridian and this is the Earth's geographic meridian, this angle is known as theta, that is declination. And this is known as magnetic meridian, and this is known as geographic meridian. And if This is the magnetic meridian, and this will be the direction, horizontal direction along the magnetic meridian. So if the net magnetic field direction of Earth's magnetic field is along this direction, if this is the B net of Earth's magnetic field, and this is the horizontal along the Earth magnetic meridian, and then its component along this direction will be known as what? Horizontal component of Earth's magnetic field, which is denoted by BH, and which is perpendicular to this, that will be along this direction. This will be known as the vertical component of Earth's magnetic field. And as we all previously discussed, that the angle between the horizontal direction and the net magnetic field at any place will known as what? Angle of inclination or angle of dip. So here, as this is the horizontal direction and this is the net magnetic field direction, so this angle at this place will be denoted by what? Phi, which is known as angle of dip or angle of inclination. So for this, if this angle will be angle of dip or angle of phi for this place, so this component of Earth's net magnetic field BH will be how much? According to the resolution of vector, this is a vector quantity, so BH will be how much? Bn cos phi. Similarly, BV, the vertical component, will be how much? Bn sin phi. Clear? So the vertical component of Earth's net magnetic field will be how much? Bn sin phi, and the horizontal component will be Bn cos phi. What is phi? This is the angle of inclination or angle of dip at that place. Clear? So from this figure, we can calculate that as the horizontal component BH will be represented as Bn cos phi, let it be equation 1, and the vertical component BV will be Bn sin phi, let it be equation 2. So from 1 and 2 we can get what? So from 1 and 2 we get BV equal to Bn sin phi dividing with BH, which is equal to how much? Bn divided by cos phi. So from 1 and 2 we get by dividing 1 with 2. Okay, so this will be how much? BV, the vertical component with horizontal component will be tan phi. This will be equal to the vertical component BV equal to BH tan phi. This is the relation between Earth's vertical component of the magnetic field and horizontal component of the magnetic field, where phi is what? The angle of dip or angle of inclination at any place. So if we have to calculate the horizontal component or vertical component of the Earth's net magnetic field at any place where the angle of dip or inclination is given, then this is the relation how we can calculate the horizontal and vertical component. So as we know, at pole phi equal to how much? 90. So if at pole phi equal to 90, so BV equal to how much? Bn sin 90, which is equal to Bn. That means at pole the vertical component of Earth's magnetic field will be equal to what? The net magnetic field. Okay, because as pole the direction of net magnetic field is vertical. Similarly, at equator phi equal to 0. So BH equal to how much? Bn cos 0, which is equal to Bn. So at equator the horizontal component of Earth's magnetic field will be equal to the net magnetic field of Earth's magnet, and as the vertical value for equator will be how much? Bn sin 0 and sin 0 will be 0. So the vertical component at Earth's equator will be 0. And similarly at pole, the horizontal component BH will be how much? BH equal to BN cos 90, which is equal to 0. So at pole, the horizontal component of Earth's magnetic field is 0, and at equator, here we can write BV equal to Bn sin 0, which is equal to 0. So at equator, BH equal to net magnetic field and BV equal to 0. At pole, BV equal to net magnetic field and BH equal to 0. That means at equator only horizontal component of the Earth's magnetic field exists, and at pole only vertical component of Earth's magnetic field exists. Clear? So this is all about the magnetic elements of Earth, that is declination, which is the angle between geographic meridian and magnetic meridian of Earth. Then inclination, which is the angle between net magnetic field direction with the horizontal direction at any place on Earth's surface, and then the horizontal component of Earth's net magnetic field, that is the component of net magnetic field of Earth's magnets along the horizontal direction of magnetic meridian, and whose value will be equal to how much? BH cos theta, as we already discussed here, and the relation between vertical component and horizontal component will be this much, where phi is what? The angle of dip or inclination. So from this discussion we already know that the net magnetic field of Earth can be divided into two parts, that is vertical and horizontal. So when we move in a horizontal plane, then the vertical component of Earth's magnetic field will only be changed, because the horizontal level will remain constant. But when we move down or vertically, then the vertical remain constant, but the horizontal component of Earth's magnetic field will get changed. Clear? And as Earth behaves as a magnet, it must have some magnetic strength, and the strength of the magnetic field produced due to Earth is nearly about 10 to the power minus 5 Tesla, which is equal to 0.1 Gauss. Okay, it's a very small quantity, or it's a very small value, but this much, nearly this much amount of magnetic field strength is produced by our planet Earth. So this is all about the magnetic effect of Earth, or how Earth behaves as a magnet, what are the elements linked with Earth's magnetism, what is the strength of Earth's magnet. And we already know the magnetic force is a very long range force, and there are many terrestrial objects which have very large magnetic strength in comparison to our planet Earth. The one of the very known is known as the Neutron Star. So this neutron star have very large amount of magnetic field strength, or this can also be known as a magnetar. Okay, so you can search about this magnetar in Google. This have a very large magnetic field strength, which is about, this is the strength of our planet Earth, which is 0.1 Gauss, and the strength of magnetar or any neutron star will be nearly about 1 trillion or quadrillion, nearly about 10 to the power 15 Gauss. So you can now imagine what is the strength of a magnetar. The magnetic strength of a magnetar is very large. This is nearly about 10 to the 15 Gauss. You can search about this in Google. So this is all about the magnetism and the magnetic elements of Earth, and the all thing that we discussed in the magnetostatics. In next class we will discuss further about this magnetic effects. Okay, so thank you.